Okay, let's go over number 7 from the non-textbook homework. This is approximating, all right, the essentially area under the curve, in this case of the function f of x equals sine of x over this interval here from 0 to pi. And we're estimating with this R6. Now, what is that? The R stands for using the right-hand endpoints. Subscript 6 means we have 6 subintervals. So I'm going to divide the interval from 0 to pi. We usually talk about from A to B, right? So A is 0, B is pi, into n equals 6, right? Equally spaced subintervals. And the width of those we call delta x, okay? And so it's just the length of the interval, which will be b minus a, or in this case, pi minus 0, right? Pi, that's how long the interval is, divided by 6. So you get pi divided by 6, pi sixth. That is the length. By the way, remember pi is about 3.14. And so this is slightly more than 1/2. The width of each of our intervals is slightly more than 1/2. I've actually written out all 6 intervals with both the left and the right endpoints. So, right, the first one will go from 0, right? This is our left endpoint 0 to what? Add pi over 6 to pi over 6. And then pi over 6 to what? If I add pi over 6 to pi over 6, I get 2 pi over 6, which I went ahead and simplified down to pi over 3. All right. Then we go from pi over 3 to what? 2 pi over 6 plus pi over 6, 3 pi over 6, which simplifies down to pi over pi halves. And then pi over 2 to 4 pi over 6, which is the same as 2 pi over 3. And then 2 pi over 3 to 5 pi over 6. And then 5 pi over 6 to what? 6 pi over 6, which of course is just pi. And you should end up with pi. Notice I've got 1, 2, 3, 4, 5, 6 intervals, right? And we should end up with pi being our right endpoint of our last interval. Okay. So, so now what we're going to do is use the right-hand endpoints, right? So I'm going to use the value of the function at pi over 6 for this first interval to approximate the area under the curve by a rectangle, right? Whose height is f of pi over 6. And then for the second interval, I use the right-hand endpoint pi over 3, and so on. I've got an arrow pointing to each of these right-hand endpoints. So what is R6 look like? It's the area of each rectangle, which is the height that for this first interval, we're going to use the right-hand endpoint pi over 6. So the height of that rectangle is f of pi over 6 times the width, which was delta x. Remember, delta x is the same for each one. So you'll see we have delta x as the width for each of these rectangles. But the height's going to vary. Right here, we use for the first interval, we use the right-hand endpoint pi over 6. For the second interval, I'll use pi over 3, f of pi over 3. To get the height, f of pi over 2, f of 2 pi over 3, and so on. So 1, 2, 3, 4, 5, 6. We get those 6 rectangles. And so now, remember, our function f was the function sine of x. So if I plug in that information, I'm going to, first of all, simplify things by obviously factoring out the delta x. Since it's common to all, I'll factor it out. And I'm just left with f of pi over 6, which is sine of pi over 6, plus f of pi over 3, which is sine of pi over 3, f of pi over 2, which is sine of pi over 2, and so on. Okay. At this point, in general, you could use your calculator to just punch in, right, these quantities and then approximate that. I went ahead and did it exact just because I realized these are common values that we know the sine of. For instance, sine of pi over 6 we know is 1/2. Sine of pi over 3 is square root of 3 over 2. Sine of pi halves is 1. Sine of 2 pi over 3 is square root of 3 over 2. Sine of 5 pi over 6 is 1/2 again, and sine of pi is actually 0. And then I just sort of did a little simplifying. So 1/2 plus 1 plus 1/2 is a total of 2. So 1 plus 1/2 plus 1/2 is 2. And the square root of 3 over 2 plus the square root of 3 over 2 is equal to the square root of 3. All right, 1/2 square root of 3 plus 1/2 square root of 3 is square root of 3. So this all in here, these 6 sums here, sine of pi over 6, sine of pi over 3, and so on, simply adds up to 2 plus the square root of 3. Pi over 6, remember, was our delta x. That was how we calculated that interval, pi over 6. And so pi over 6 times 2 plus the square root of 3 is 1.954. Now I did that in my calculator both ways, so you can see I actually entered in the let me just actually re-enter that first one there. You could see I did pi over 6, right, times, I put that in parentheses, and then in parentheses, I did the sine of pi over 6 plus the sine of pi over 3 plus the sine of pi over 2 and so on. Making sure, of course, you want to make sure in mode, if you hit mode, that you're in radian mode when we're dealing with trig functions, okay? So I did all that, and I get, of course, the same thing, rounded off 1.9, 1.954. And then if I, or just enter in my simplified expression here, I sort of reverse the order, but 2 plus the square root of 3 in parentheses times pi over 6 gives me the same thing. So that's the result. Now, geometrically, what's going on here? Here is the graph of the sine function. All right, this is f of x equals sine of x. This is the graph of the sine function. Of course, it's going up and down, remember, oscillating between 1 and -1. But on the interval from 0 to pi, it's always positive. It's always above the x-axis. All right, and so again, we know that sine of 0 is 0, sine of pi over 6 is a half, sine of pi over 3 is square root of 3 over 2, sine of pi over 2 is 1, and then sine of 2 pi over 3 is square root of 3 over 2, sine of 5 pi over 6 is a half, and so on. And I went ahead and drawn the rectangles, right, that we're finding the area of in the R6 sum. So in the first subinterval from 0 to pi over 6, we used the right-hand endpoint, and the height, f of pi over 6, right, was a half. So here, this is this black rectangle here. That's what I'm getting for this first, right? That's the 1/2 times the width, which would be pi over 6, right? That gives me the area of that rectangle. And then, you know, f of pi over 3, the height times delta x will give me the area of the second rectangle, right? And so on, third rectangle, fourth rectangle, fifth. Where's the sixth one? Well, remember, sine of pi is 0, so the height is actually 0. So, you know, we're just getting 0 for our estimate here. So what we're trying to do again with these sums is estimate really the area under this red curve. So if I think about that area, let me shade in that area. Here's what we're trying to estimate, right? And so we're estimating it with the area of these 5 rectangles, really, although the 6th one is just 0, but you can sort of see how that works. Now, to get a better estimate, of course, we can increase n, the number of subintervals, and as we do so, we find that we get a better and better approximation. But right now, when I'm doing a finite sum, R6, R5, R4, or L, you know, using left-hand endpoints, or M using midpoints, where there's a fixed number, I don't want to use any summation notation. Notice I didn't use any summation notation, right? I just list out, I get my delta x, and then I get all my endpoints, right? And they're all delta x apart from one another, right? 0 to pi over 6, pi over 6 more gives me pi over 3, pi over 6 more gives me pi over 2, and so on. I just list all those out, and then I make sure I use, you know, if it's R, I use the right-hand endpoints. If this was L, if this was L6, if this was L6, then I would be using what? I would start with 0. I would have f of 0 here first, and then f of pi over 6, and then f of pi over 3, and then pi over 2, then 2 pi over 3. And I would stop at 5 pi over 6. I would not include pi, right, as one of the inputs for the heights of my rectangles. And if you did midpoint, you would have to find the midpoint. You'd have to find halfway between 0 and pi over 6, which is actually going to be what, pi over 12, right? And then so on. You would find the midpoint in each of these, and that would give you the height of your rectangle. Okay, but that's the way you want to do each one of these, and hopefully this one is helpful.